Subatomic physics, otherwise known as nuclear physics. This reindeer sled carries the tusk of a 20,000-year-old woolly mammoth found in Russia. Scientists used a process called carbon dating to estimate the mammoth's age. All living organisms have the same ratio of carbon-14 atoms to carbon-12 atoms. The carbon-14 atoms decay into other atoms when an organism dies. Thus, the ratio of carbon-14 to carbon-12 can be used to date the organism. Chapter illustration. The tusks shown in this photograph are from a 20,000-year-old woolly mammoth that was discovered in the Taymyr Peninsula of Siberia, Russia. The mammoth was named Jarkov after the indigenous Dolgan tribesmen who first discovered the tusks sticking out of the snow. A 23-ton block of ice containing the mammoth was chiseled from the peninsula and flown to an ice tunnel to study. It was originally believed that the mammoth was preserved fully intact. However, as scientists thawed the ice block with hair dryers, they learned that the ice contained only scattered remains of the mammoth. Section 1, the nucleus, discusses properties of the atomic nucleus, identifies mass number, atomic number, and neutron number, explains why some nuclei are unstable, and shows how to calculate binding energy. Section 2, nuclear decay, describes the three types of radioactive decay, shows how to predict the outcome of nuclear decay, defines the decay constant, and shows how to calculate the half-life of a radioactive substance. Section 3, nuclear reactions, distinguishes between nuclear fission and nuclear fusion and explores nuclear chain reactions. Section 4, particle physics, discusses the four fundamental interactions of nature and their mediating particles, classifies the elementary particles that make up matter, and describes the standard model of the universe. The force between two charges is proportional to the magnitudes of the charges and inversely proportionate to the distances between them squared. Atoms consist of a positive nucleus surrounded by negatively charged electrons. Study the equation, it will become useful in this chapter. Chapter preview, the nucleus. Section 1, broken into two subsections, properties of the nucleus and nuclear stability. Section 2, nuclear decay, broken into three sections, nuclear decay modes, nuclear decay series, and measuring nuclear decay. Section 3, nuclear reactions, is simply one subsection, fission and fusion. Particle physics is three sections, the particle view of nature, classification of particles, and the standard model. What to expect? In this chapter, you will study the atomic nucleus, radioactive decay, and the process of fission and fusion. You will also learn about the standard model of the universe, why it matters. Radioactive decay makes it possible to date organic materials that are 1,000 to 25,000 years old. Nuclear fission is an important energy source today, and nuclear fusion may be an important energy source for the future. Objectives, Section 1, the nucleus. Identify the properties of the nucleus of an atom. Explain why some nuclei are unstable. And 3, calculate the binding energy of various nuclei. Properties of the nucleus. In the chapter, Electric Forces and Fields, you learn that atoms are composed of electrons, protons, and neutrons. Except for the ordinary hydrogen nucleus, which consists of a single proton, both protons and neutrons are found in the nucleus. Together, protons and neutrons are referred to as nucleons, as seen in the chapter Atomic Physics. Rutherford scattering experiment led to the conclusion that all of an atom's positive charge and most of its mass are concentrated in the nucleus. Rutherford's calculations revealed that the nucleus has a radius of no greater than about 10 to the negative 14 meters. Because such small lengths are common in nuclear physics, a convenient unit of length is the femtometer, FM. Misconception alert. Students might not distinguish between the order of magnitudes involved at the atomic and nuclear levels. Point out that the size of the nuclear radius is about 10 to the negative 14 meters. This is approximately 10,000 times smaller than the radius of the atom. Although the nucleus is much smaller than the atom, the energies involved in nuclear processes such as radioactivity are 1,000,000 times higher than the energies exchanged in atomic processes, such as the release of photoelectrons. Table 1, symbols for nuclear quantities. It would be helpful to study this, although you may know this from chemistry. Sometimes called the Fermi, this unit is equal to 10 to the negative 15 meters. A nucleus can be specified by an atomic number and an atomic mass. There are a few important quantities that are used to describe the charge and mass of the nucleus. Table 1 lists these quantities and the symbols commonly used to represent them. The mass number A represents the total number of protons and neutrons, or nucleons, in the nucleus. The atomic number Z represents the number of protons in the nucleus, and the neutron number N, capital N, represents the number of neutrons in the nucleus. Note that A, Z, N are always integers. As an example, a typical atom of aluminum has a mass number A of 27 and an atomic number Z of 13. Therefore, it has 13 protons and 14 neutrons and an atomic mass number of 27. That means that it would have 14 neutrons because 27 minus 13, the number of protons, is 14. Here is a picture of aluminum. Notice the superscripts on the left of the symbol. The top superscript is the mass number. The bottom is the subscript is the atomic number, Z, the number of protons. A periodic table of the elements usually includes the atomic number of each element above or near the element's chemical symbol. Frequently, the mass number and the atomic number of the nucleus of an atom are written before the atom's chemical symbol, as shown in Figure 1. The chemical symbol for aluminum is Al. The superscript refers to the mass number, A, 27 in the case of aluminum, and the subscript refers to the atomic number, Z, 13 in the case of aluminum. An element can be identified by its atomic number, Z. Because the number of protons determines the element, the atomic number of any given element does not change. Thus, the chemical symbol, such as Al, or the name of the element, such as aluminum, can always be used to determine the atomic number. For this reason, the atomic number is sometimes omitted. Although atomic number does not change within an element, atoms of the same element can have different mass numbers. This is because the number of neutrons in a particular element can vary. Atoms that have the same atomic number but different neutron numbers, and thus different mass numbers, are called isotopes. An isotope, an atom that has the same number of protons or the same atomic number as other atoms of the same element, but that has a different number of neutrons, and thus a different atomic mass or mass number. The neutron number for an isotope can be found from the following relationship. A equals Z plus N. This expression says that the mass number of the atom A equals the number of protons Z plus the number of neutrons N in the nucleus of the atom. Study these little equations. They can be helpful in determining certain aspects of the atomic structure. The natural abundance of isotopes can vary greatly. For example, carbon 11, carbon 12, carbon 13, and carbon 14 are 4 isotopes of carbon. The natural abundance of carbon 12 isotope is about 98.9%, while that of carbon 11 isotope is about 1.1%. Some isotopes do not occur naturally but can be produced in the laboratory. Even the simplest element, hydrogen, has isotopes. Hydrogen 1 called hydrogen or protium, hydrogen 2 called deuterium or heavy hydrogen, and H3 called tritium or heavy hydrogen. Figure 2, a nucleus can be visualized as a cluster of tightly packed spherical protons and neutrons. This illustration is just a representation. Nucleons actually fill very little of the volume of the nucleus and are in rapid motion. A nucleus is very dense. Experiments have shown that most nuclei are approximately spherical and that the volume of a nucleus is proportional to the total number of nucleons, and thus to the mass of the nucleus. This suggests that all nuclei have nearly the same density, which is about 2.3 times 10 to the 17th kilograms per cubic meter, which is 2.3 times 10 to the 14th times greater that of the density of water, which is 1 times 10 to the third kilograms per cubic meter. Nucleons combine to form a nucleus as though they were tightly packed spheres, as shown in Figure 2. The symbol U represents the unified mass unit, also known as the atomic mass unit. Some texts use the symbol AMU to represent this unit. The unified mass unit and rest energy are used to express the mass of a nucleus. Because the mass of a nucleus is extremely small, the unified mass unit, U, is often used for atomic masses. This unit is sometimes referred to as the atomic mass unit. 1U is defined so that 12U is equal to the mass of one atom of carbon 12. That is, the mass of a nucleus or atom is measured relative to the mass of an atom of a neutral carbon 12 isotope, the nucleus plus 6 electrons. Based on this definition, 1U equals 1.6605386 times 10 to the negative 27th kilogram. The proton and neutron each have a mass of around 1U, and the electron has a mass that is only a small fraction of the unified mass unit, about 5 times 10 to the negative 4 U. Misconception alert. To help students differentiate between atomic mass and mass number, explain that the periodic table gives the atomic number and the atomic mass rather than the mass number of each element. Ask students if both mass numbers given on the periodic table are integers. Atomic numbers are, atomic masses are not. Explain that the atomic mass reported on the periodic table is an average of many nuclei with the same atomic number, but different mass numbers. Mass number, on the other hand, relates to an individual nucleus and is always an integer. Alternatively, the mass of a nucleus is often expressed in terms of rest energy. A particle has a certain amount of energy, called rest energy, associated with its mass. The following expression expresses the relationship between mass and rest energy mathematically. Relationship between rest energy and mass. Rest energy equals mass times the speed of light squared. Because the rest energy of a particle is given by ER equals mc squared, it is convenient to express the particle's mass in terms of energy equivalent. The equation that follows is for the rest energy of a particle with a mass of exactly 1 U. ER equals mc squared. And there is an example problem. Thus, the conversion of 1 U of mass into energy would produce about 931.49 mega electron volts. Here's table 2, mass and rest energy of atomic particles. Actually, fairly interesting. This book will use the value 931.49 mega electron volts for calculations. Recall that M is the abbreviation for the SI prefix mega, which indicates 10 to the 6th. The masses and energy equivalent of the proton, neutron, and electron are summarized in Table 2. Did you know the equivalence between mass and energy is predicted by Einstein's special theory of relativity? Another aspect of this theory is the time and length are relative. That is, they depend on the observer's frame of reference, while the speed of light is absolute. Notice that in order to distinguish between mass of the proton and mass of the neutron, you must know their masses to at least 4 significant figures. The masses and some other properties of selected isotopes are given in Appendix H. Explain to students that no particle has exactly 1 U of rest energy. The masses of the proton and neutron are only approximately equal to 1 U. Emphasize that 1 U times c squared equals 931.49 mega electron volts. Have students compare this value to the rest energies of the proton and neutron. As seen in the chapter Atomic Physics, the electron volt, EV, is a unit of energy typically used to describe atomic processes. 1 electron volt equals 1.60 times 10 to the negative 19 joules. Because energies at the nuclear level are much greater than those at the atomic level, units of mega electron volt, or M equals 1 times 10 to the 6th, are often more convenient. 1 mega electron volt equals 1 times 10 to the 6th times 1.60 times 10 to the negative 19 joules equals 1.6 times 10 to the negative 13 joules. Nuclear stability. Given that the nucleus consists of closely packed collection of protons and neutrons, you might be surprised that it can exist. It seems that the Coulomb repulsion between protons would cause a nucleus to fly apart. There must be some attractive force to overcome this repulsion force. This force is called the nuclear force, or the strong force. Strong force, the interaction that binds nucleons together in a nucleus. Figure 3, each data point in this graph represents a stable nucleus. Note that as the number of protons increases, the ratio of neutrons to protons also increases. In other words, heavy nuclei have more neutrons per proton than light nuclei. Study this graph very carefully. It shows the stability, how when things get very heavy at the top, things are going to start to fall apart. Figure 3, visual strategy. Point out that the solid red line is only a reference line. It shows that instead of having equal number of protons and neutrons, most stable nuclei have more neutrons than protons. The stable nuclei are represented as clusters of dots rather than as a line, because all nuclei have an integral number of protons. For example, there are no stable nuclei between 50 and 51 because it is impossible to have an element with 50.5 protons. Also, have students notice that More than one isotope may be stable. Question. Some dots on the empirical graph form vertical lines. What do these dots represent? Multiple dots on a vertical pattern represent isotopes of nuclei of the same element. For example, with Z equals 48, cadmium, the nucleus may contain 58, 60, 62, 63, 64, 65, 66, or 68 neutrons. The strong force has some properties that make it very much unlike other types of force. The strong force is almost completely independent of electric charge. For a given separation, the force of attraction between two protons, two neutrons, or a proton and a neutron has the same magnitude. Another unusual property of the strong force is it is very short range, only about 10 to the negative 15 meters. For longer distances, the strong force is virtually zero. Neutrons help to stabilize a nucleus. A plot of neutron number versus atomic number, the number of protons for stable nuclei, is shown in figure 3. The solid line in the plot shows the location of the nuclei that have an equal number of protons and neutrons, n equals z. Notice that only light nuclei are on this line, while all heavier nuclei fall above this line. This means that heavy nuclei are stable only when they have more neutrons than protons. This can be understood in terms of the characteristics of a strong force. For a nucleus to be stable, the repulsion between positively charged protons must be balanced by the strong nuclear force's attraction between all the particles in the nucleus. The repulsive force exists between all protons in a nucleus because the electrostatic force is long range. But a proton or a neutron attracts only the nearest neighbors because of the nuclear force is short range. So as the number of protons increases, the number of neutrons has to increase even more to add enough attractive forces to maintain stability. For Z greater than 83, the repulsive force between protons cannot be compensated by the addition of more neutrons. That is, elements that contain more than 83 protons do not have stable nuclei. The long, narrow region in figure 3 on the previous page, which contains the cluster of dots representing the nuclei, is sometimes referred to as the valley of stability. Language of physics. Make sure that students interpret the symbols and subscripts of the equations correctly. Ask how the total mass changes when a helium nucleus is broken down into the components of the two protons and two neutrons. The total increase by the mass defect, delta M. Mass defect, delta M. Got it. Check. Nuclei that are not stable decay into other nuclei until the decay product is one of the nuclei located in the valley of stability. A stable nucleus's mass is less than the masses of its nucleons. The particles in the stable nucleus are held tightly together by the attractions of the strong nuclear force. In order to break such a nucleus apart into separated protons and neutrons, energy must be added to overcome the force's attraction. For most nuclei, the particles bound together in the nucleus have a lower energy state than the same set of particles would have if they were separated, because they are so much higher in energy. Isolated protons and neutrons are very, very rare. The quantity of energy needed to break a nucleus into individual unbound nucleons is the same as the quantity of energy released when unbound nucleons come together to form a stable nucleus. This quantity of energy is called the binding energy of the nucleus. Binding energy, the energy released when unbounded nucleons come together to form a stable nucleus. This quantity of energy is called binding energy of the nucleus. Binding energy. The energy released when unbound nucleons come together to form a stable nucleus, which is equivalent to the energy required to break the nucleus into individual nucleons. It is equal to the difference in energy between the nucleons when bound and the same nucleons when unbound. To bound or not to bound? That is the question. Note that except for very small values of A, unbound nucleons do not simply combine into full-grown nucleus, a full-grown nucleus. Binding energy can be calculated from the rest energies of the particles making up a nucleus as follows. E bind equals ER unbound minus ER bound. Using the equation for rest energy, we can rewrite this as follows. E bind equals M unbound C squared minus M bound C squared equals the quantity M unbound minus M bound times, all times, C squared. The mass of the nucleons when unbound minus the mass of the nucleons when bound is called the mass defect and is expressed as delta M. Thus, the previous equation for binding energy can be expressed as follows. Binding energy of a nucleus equals mass defect times speed of light squared. Note that the total mass of a stable nucleus, M bound, is always less than the sum of the masses of its individual nucleons, M unbound. It is often useful to find the mass defect in terms of U, so that it can be converted to energy as described earlier in this chapter. 1 U, or 1 atomic mass unit, equals 931.49 mega electron volts. The mass of the unbound nucleus is the sum of the individual nucleon masses, and the mass of the bound nucleus is about equal to the atomic mass minus the mass of the electrons. Thus, the change in mass equals ZMP plus NMN minus atomic mass minus ZME. Misconception alert. Students may wonder whether elements with Z greater than 83 exist because these elements are unstable and do not appear in figure 3 on the previous page. After the concept of half-life has been introduced in section 2, point out that the half-lives of unstable elements vary from fractions of a second to thousands of years. Thus, some unstable elements exist for very long periods of time. One way to rearrange this equation is delta M equals ZMP plus ZME plus NMN minus atomic mass. Misconception alert. Some students may think that binding energy is present in the nucleus. Emphasize that binding energy is the amount of energy required to break the nucleus into its component parts, which destroys its structure. Explain that because very light and very heavy elements have the least binding energy, they are the only elements for which we can extract energy. These concepts are discussed further in section 3. Because a hydrogen atom contains one proton and one electron, the first term is equal to Z, atomic mass of H, or hydrogen. Thus, the equation for mass defect can be written as follows. Delta M equals Z, atomic mass of hydrogen, plus NMN minus atomic mass. Use this equation and the atomic mass given in Appendix H to calculate mass defect when solving problems involving binding energy. In this discussion, we have disregarded the binding energies of the electrons. This is reasonable because nuclear binding energies are many tens of thousands of times greater than electronic binding energies. The binding energy per nucleon for light nuclei, A is less than 20, is much smaller than the binding energy per nucleon for heavy nuclei. In other words, particles in lighter nuclei are less tightly bound on average than particles in heavy nuclei. Except for the lighter nuclei, the average binding energy per nucleon is about 8 megaelectron volts. Of all nuclei, iron 58 has the greatest binding energy per nucleon. The nucleus of deuterium atom, called deuterion, consists of a proton and a neutron. Given that the atomic mass of deuterium is 2.014102 atomic mass units, calculate the deuterion's binding energy in mega electron volts. Well, what is given? The fact that Z equals 1, it's hydrogen, there's one proton. The atomic mass is given. N equals 1 means it has one neutron. And the atomic mass of hydrogen is 1.007825 U. And so the unknown is going to be the binding energy. Choose an equation or situation. First, find the mass defect with the following relationship. And that's the relationship that was in the section. Then find the binding energy by converting the mass defect to rest energy. Substitute the values into the equation and solve. There's the plug-in. And there is the mass defect. All right, so the E-bind equals 2.224 mega electron volts. 2.224 mega electron volts. In order for deuteron to be separated into its constituents, a proton and neutron, 2.224 mega electron volts of energy must be added. Calculate the total binding energy of neon 20 and calcium 40. Refer to Appendix H for this and the following problems. For neon 20, you have the Z and the A. The atomic mass is 19.992435 U, and then the atomic mass of hydrogen is also given. You have the Mn given, and the Z for calcium, the A for calcium. So it's putting down all of the givens. And now the delta M is being given. And that's going to be ultimately 0.172465. And then the E-bind is going to be 160.65 mega electron volts. And now, this is for calcium, and the delta M is going to be 0.367209 U, and the E bind is going to be 342.05. Determine the difference in the binding energy of hydrogen 3 and helium 3. All right, hydrogen 3, that's the Z and the A. The atomic mass of hydrogen 3, the atomic mass of hydrogen. Remember, hydrogen is protium. You have protium, deuterium, and tritium. You have helium 3, A and Z, and the atomic mass of helium 3, and the delta M is going to be, looks like for helium 3, is going to be 0.009106 U, and the E bind is going to be 8.482 mega electron volts. And the delta M is going to be 0.008286. The E bind is 7.718 mega electron volts. The difference in binding energy is 0.764 mega electron volts. Calculate the binding energy of the last neutron in calcium 43 nucleus. Compare the mass of calcium 43 with the mass of calcium 42 plus the mass of a neutron. That's a hint. The atomic mass of calcium 43, the Mn, the atomic mass of calcium 42, the delta M will be, all right, 0.008516, and the E bind of the last electron will be 7.933 mega electron volts. Find the binding energy per nucleon of uranium-238 in mega electron volts. All right, that is uranium-238. There's the Z. Coming up is the A, uranium-238. And the atomic mass of U-238 and the mass of hydrogen, the Mn, and then the neutrons, 146. The delta M will be 1.934206, and the E bind per nucleon. The E bind per nucleon, very important number. The E bind per nucleon will be 7.5701 mega electron volts per nucleon. Does the nuclear mass of the charge of the nucleus determine what element an atom is? The charge of the nucleus, the atomic number. Oxygen has several isotopes. What do these isotopes have in common? How do they differ? They have the same number of protons and electrons. They have a different number of neutrons and hence a different number of nucleons. Of atomic number, mass number, and neutron number, which are the same for each isotope of an element and which are different? Z is the same for each isotope. A and N are different. The protons in a nucleus repel one another with a Coulomb force. What holds these protons together? The strong force. Describe the relationship between the number of protons and the number of neutrons and the stability of the nucleus. For light nuclei, n is approximately equal to z. As the number of protons increases, more neutrons per proton are needed to compensate for the Coulomb repulsion, so n is greater than z. Calculate the total binding energy of the following. Niobium-93, referred to Appendix H. There's the atomic mass of hydrogen. There's the Mn. Niobium-93, there's the Z and the A. Atomic mass. The N, number of neutrons is 52. Delta M is going to be 0.865029 U, and the E bind is going to be 805.77 electron volts. Calculate the total binding energy of the following. Gold 197, referred to Appendix H. There's gold 197, and the A and the Z. The Z is 79, and the A is 197. The atomic mass of gold, number of neutrons 118, the delta M is going to be 1.674102, and the E bind is going to be 1559.4 mega electron volts. Calculate the total binding energy of Aluminum-27, referred to Appendix H. There's the Z, it's 13, 27 is the mass number, and 14 neutrons. The delta M going to be 0.241501, the E bind. And the E bind is 224.96 mega electron volts. How many protons are there in the nucleus of carbon-14? How many neutrons and how many electrons are there in the neutral atom? There are 6 protons, 8 neutrons, and 6 electrons in the neutral atom. 2 isotopes having the same mass number are known as isobars. Calculate the difference in binding energy per nucleon for the isobars sodium-23 and magnesium-23. How do you account for this difference? All right, let's start with sodium and run through it, and then we'll do magnesium. It says calculate the difference in binding energies per nucleon for the isobars. So here is Z and the A and the atomic mass. Here's the atomic mass of hydrogen, right on track. Here's the Mn. Here is magnesium-23. There's the Z, of course, for magnesium. And it's 23 is A. I'll clear some space here. So we have all the information we need up top for sodium and magnesium 23. Now we're calculating the delta M for sodium 23, and that's going to be 0.20029. And next, we want to calculate, we want to calculate for magnesium. N is 11 for magnesium, and delta M is 0.195091. So we will bring forward the delta M for sodium, the delta M for magnesium. This is the E bind per nucleon for sodium, the E bind per nucleon for magnesium. And then the difference is 0.2106 mega electron volts. So clearly, the difference in binding energy per nucleon is, between sodium and magnesium, 0.2106 mega electron volts. Now let's decide why that difference is so. And it says, how do you account for this difference? How do you account for the difference? 0.2106 mega electron volts because of the extra proton in magnesium 23. The Coulomb repulsion in the magnesium nucleus is greater than that in the sodium nucleus, thus breaking the magnesium nucleus into its components requires less energy. In other words, its binding energy is less. Section 2, nuclear decay. Describe the three modes of nuclear decay, predict the products of nuclear decay, and last, 3, calculate the decay constant and the half-life of a radioactive substance. Nuclear decay modes. So far, we have considered what happens when nucleons are bound together to form stable nuclei. Some students may think that binding energy is present in the nucleus. Emphasize that binding energy is the amount of energy required to break the nucleus into its component parts, which destroys its structure. Explain that because very light and very heavy elements have the least binding energy, they are the only elements for which we can extract energy. This concept is discussed further in section 3. Students may not understand why there are only 109 known elements, but 400 stable nuclei have been identified. To clarify their understanding, have students review the meaning of isotopes introduced in section 1 and list examples. The radioactive decay of radium nuclei causes the hands and numbers of this watch to glow in the dark. However, not all nuclei are stable. There are about 400 stable nuclei. Hundreds of others are unstable and tend to break apart into other particles. This process is called nuclear decay. The nuclear decay process can be a natural event or can be induced artificially. In either case, when a nucleus decays, radiation is emitted in the form of particles, photons, or both. The emission of particles and photons is called radiation, and the process is called radioactivity. For example, the hands and numbers of the watch shown in figure 4 contain small amounts of radium salts. The nuclei within these salts decays, releasing light energy that causes the watch to glow in the dark. Here are the particles that exist in nuclear decay, the main particles, alpha, beta, and gamma radiation. Study this carefully. This would be very informative. The nucleus before decay is called the parent nucleus, and the nucleus remaining after decay is called the daughter nucleus. In all nuclear reactions, the energy released is found by the equation E equals delta m, change in mass, times the speed of light squared. A radioactive material can emit three types of radiation. Three types of radiation can be emitted by the nucleus as it undergoes radioactive decay. Alpha particles, in which the emitted particles are helium nuclei, beta particles, in which the emitted particles are either electrons or positrons, positively charged with a mass equal to that of an electron, and gamma rays, in which the emitted rays are high energy photons. These three types of radiation are summarized in Table 3. The ability of radiation to pass through a material depends on the type of radiation. Alpha particles can usually be stopped by a piece of paper. Beta particles can penetrate a few millimeters of aluminum, and gamma rays can penetrate several centimeters of lead. Helium nuclei are emitted in alpha decay. When a nucleus undergoes alpha decay, it emits alpha particles, which is the helium nucleus. Thus, the nucleus loses 2 protons and 2 neutrons. This makes the nucleus lighter and decreases its positive charge. Because the electrons around the nucleus do not participate in nuclear reactions, they are ignored. Look at a periodic table and pick a radioactive element, and you can count by twos. And these are some of the nuclei that the substances break down to. Here's Table 4, Rules for Nuclear Decay, very informative and very important. For example, the nucleus of uranium-238 can decay by alpha emission to thorium-234 nucleus and an alpha particle as follows. Uranium-238 yields thorium-234 plus helium-4. This expression says that a parent molecule, uranium-238, emits an alpha particle, helium-4, and thereby changes to a daughter nucleus, thorium-234. This nuclear reaction and all others follow the rules summarized in Table 4. These two rules can be used to determine the unknown daughter atom when a parent atom undergoes alpha decay. Electrons or positrons are emitted in beta decay. When a radioactive nucleus undergoes beta decay, the nucleus emits either an electron or a positron. In the equation for beta decay, the symbol, beta particle, suggests that the mass of the electron is 0. This may seem to contradict students' prior understanding of atomic physics. Explain that the 0 means that the electron's mass is negligible compared with the other masses involved in nuclear decay. Also emphasize that in beta decay, the daughter nucleus has the same mass number that the parent does. In other words, the daughter contains the same number of nucleons that the parent does. A positron has the same mass as an electron, but is positively charged. The atomic number is increased or decreased by 1 with an opposite change in the neutron number. Because the daughter nucleus contains the same number of nucleons as the parent nucleus, the mass number does not change. Thus, beta decay does little to change the mass of the nucleus. Instead, the ratio of neutrons to protons in the nucleus is changed. The ratio affects the stability of the nucleus as seen in Section 1. A typical beta decay involves carbon-14 as follows. Carbon-14 yields nitrogen-14 plus a beta particle, partial equation. This decay produces an electron written as a beta particle. In this decay, the atomic number of the daughter nucleus is increased by 1. Figure 5, the spiral in this bubble chamber image is the track left by a positron. This reaction took place in a magnetic field, which caused the positron to spiral as it lost energy. Another beta decay event involves nitrogen 12 as follows. Nitrogen 12 yields carbon 12 plus a positron. This decay produces a positron, written as a positron. In this decay, the atomic number of the daughter nucleus is decreased by 1. The superscripts and subscripts on the carbon and nitrogen nuclei follow our usual conventions, but those on the electron and the positron may need some explanation. The -1 indicates that the electron has a change whose magnitude is equal to that of a proton, but is negative. Similarly, a +1 indicates that the positron has a charge that is equal to that of a proton in magnitude and sign. Thus, the subscript can be thought of as the charge of the particle. The 0 used for the mass number of the electron and the positron reflects the fact that electrons and positrons are not nucleons. Thus, their emission does not change the mass number. Notice that both subscripts and superscripts must balance in the equations for beta decay, just as in alpha decay. Beta decay transforms neutrons and protons. A bubble chamber image of a positron is shown in figure 5. The emission of electrons or positrons from a nucleus is surprising because the nucleus is made of only protons and neutrons. Table 5, properties of a neutrino, or properties of the neutrino. Very significant. This apparent discrepancy can be explained by noting that in a beta decay, either a neutron is transformed into a proton, creating an electron in the process, or a proton is transformed into a neutron, creating a positron in the process. These two beta decays can be written as follows. Decay events can be written in this way because other particles in the nucleus, much like the electrons around the nucleus, do not directly participate in the beta decay. The electrons and positrons involved in beta decay, on the other hand, are produced in the nuclear decay process because they do not come from the shells around the nucleus. They cannot be ignored. Neutrinos and antineutrinos are emitted in beta decay. Before we conclude our discussion of beta decay, there is one problem that must be resolved. In analyzing the experimental results of beta decay reactions, scientists noticed a disturbing fact. If carbon-14 beta decay actually occurred as described on the previous page, energy, linear momentum, and angular momentum would not be conserved. In 1930, to solve this problem, Wolfgang Pauli proposed that a third particle must be missing from the equation. He reasoned that this new particle, called a neutrino, is necessary to conserve energy and momentum. Experimental evidence confirmed the existence of such a particle in 1956. The Greek letter nu is used to represent a neutrino. When a bar is drawn above the nu, the particle is an antineutrino, or an antiparticle of a neutrino. The properties of the neutrino are summarized in Table 5. I included the table 5 here again for your review. Note that the neutrino has no electric charge and that its mass is very small, perhaps even zero. As a result, the neutrino is difficult to detect experimentally. With the neutrino, we can now describe the beta decay process of carbon-14 in a form that takes energy and momentum conservation into account as follows. According to this expression, carbon-14 decays into a nitrogen nucleus, releasing an electron and an antineutrino in the process. The decay of nitrogen-12 can also be rewritten as follows. Here we see that when nitrogen-12 decays into carbon-12, a positron and a neutrino are produced. To avoid confusing these two types of beta decay, keep in mind this simple rule. In beta decay, an electron is always accompanied by an antineutrino, and a positron is always accompanied by a neutrino. High energy photons are emitted in gamma decay. Very often, a nucleus that undergoes radioactive decay, either alpha or beta, is left in an excited energy state. The nucleus can then undergo a gamma decay in which one or more nucleons makes transition from a higher energy level to a lower energy level. In the process, one or more photons are emitted. Such photons, or gamma rays, have very high energy relative to the energy of visible light. The process of nuclear de-excitation, or gamma decay, is very similar to the emission of light by an atom, in which an electron makes a transition from a state of higher energy to a state of lower energy, as discussed in the chapter on atomic physics. The word neutrino means little neutral one. It was suggested by the physicist Enrico Fermi because the neutrino had to have zero electric charge and little or no mass. Note that in gamma decay, energy is emitted, but the parts of the nucleus are left unchanged. Thus, both the atomic number and the mass number stay the same. Nonetheless, gamma decay is still considered to be a form of nuclear decay because it involves protons and neutrons in the nucleus. Two common reasons for a nucleus being in an excited state are alpha and beta decay. The following sequence of events represents a typical situation in which gamma decay occurs. Boron 12 yields carbon 12, a beta particle, and an antineutrino. The first step is a beta decay in which boron 12 decays into carbon 12. The asterisk indicates that the carbon nucleus is left in an excited state following the decay. The excited carbon nucleus then decays in the second step to the ground state by emitting a gamma ray. And then you have carbon 12 yields carbon 12 plus the gamma ray on the right side. Because the gamma decay follows the beta decay immediately, the two processes are sometimes expressed in a single equation. Misconception alert. Students may not understand how the antineutrino is able to be the neutrino's antiparticle because both have charges of zero. The neutrino also has an antiparticle called an antineutrino. Explain that in addition to charge, antiparticles are opposite their corresponding particle in quantum angular momentum, also called spin. Figure 6. The heaviest nuclei in the graph of all stable nuclei A are represented by the black dots in the enlarged view B. Note that an unstable nucleus represented by the red dots will continue to decay until the daughter nucleus is stable. And this is A. And there is the caption again. You have A and B. And try to follow the graph. Try to follow the various decays. Figure 6, visual strategy. Be sure students understand the relationship between the two parts of this figure. Point out that the numbers shown next to each chemical symbol on the graph in B are mass numbers, A, Z plus N. For example, with lead, 82 plus 186 equals 208. Question: why does alpha decay move the plot of the number of particles in the nucleus 2 squares to the left and 2 squares down? When an alpha particle is emitted, the nucleus loses 2 protons and 2 neutrons. That gives Z minus 2, 2 squares to the left, and N minus 2, 2 squares down. It's kind of like playing Battleship. Write the nuclear reaction showing the decay of Ra-228 and Ac-228. All right, there's the equation for the decay of radium-228. Can you tell from the graph in B whether gamma radiation was emitted? No. The graph only shows changes in mass and charge. Gamma rays have neither, so the energy released by gamma radiation is not shown on this representation. Nuclear decay series. If the product of a nuclear decay is stable, the decay process ends. In other cases, the decay product, the daughter nucleus, is itself unstable. The daughter nucleus then becomes the parent nucleus for an additional decay process. Such a sequence is called a decay series. Figure 6a depicts the number of protons versus neutrons for all stable nuclei. A small portion of this graph is enlarged in figure 6b, which shows a naturally occurring decay series. This decay series begins with thorium and ends with lead. Each square in figure 6b corresponds to a possible nucleus. The black dots represent stable nuclei, and the red dots represent unstable nuclei. Thus, each black dot in figure 6b corresponds to a data point in the circled portion of figure 6a. The decay series continues until a stable nuclei is reached. In this case, lead-208, notice that there is a branch in the decay path. There are actually 2 ways that thorium can decay into lead. The entire series in figure 6b consists of 10 decays, 6 alpha decays and 4 beta decays. When an alpha decay occurs, the nucleus moves down 2 squares and to the left 2 squares because it loses 2 protons and 2 neutrons. When beta decay occurs, the nucleus moves down 1 square and to the right 1 square because it loses 1 neutron and gains 1 proton. Gamma decays are not represented in this series because they do not alter the ratio of protons to neutrons. In other words, gamma decays do not change the atomic number or the neutron number. Note that the result of the decay series is to lighten the nucleus. The element radium was first discovered by Marie and Pierre Curie in 1898. One of the isotopes of radium, radium-226, decays by alpha emission. What is the resulting daughter element? Given, the decay can be written symbolically as follows. You get the radium-226, and then you have this X plus the alpha particle. The daughter element is X, and you're simply going to use a little bit of basic math. The mass numbers and atomic numbers on the two sides of the expression must be the same so that both charge and nucleon number are conserved during the course of this particular decay. So you're simply going to subtract 226 minus 4 and 88 minus 2. So mass number of X equals 226 minus 4, and then X, and 88 minus 2 is 86. And that is radon. So the daughter cell is radon, which in itself is radioactive. The periodic table shows that the nucleus with the atomic number of 86 is radon. Thus, the decay process is as follows. There it is. And the X becomes radon. Nuclear decay. Practice B. Complete this radioactive decay formula. Boron 12 yields what? You're going to have a beta decay. Refer to Appendix G for this problem and the following problems. So it's going to be 12 is going to be the mass number, and 6 is going to be the atomic number, so it'll be carbon 12. Carbon because it's 6. Complete this radioactive decay formula. Okay, so it's going to be 225 minus 221 equals 4. And that obviously is going to be helium. So that'll be an alpha decay. Complete this radioactive decay formula. You had a beta decay, so it came from carbon 14. It looks like. And it's carbon 14. Complete this radioactive decay formula. And that too is going to be looks like a repeat. That looks like it's going to be a alpha decay. And then nickel 63 decays by beta emission to copper 63. Write the complete decay formula for this process. Beta decay involves an electron and an antineutrino. So there's the antineutrino and the beta particle, and there is nickel becomes copper. You're going to get a rise in the number of protons. So the isotope iron 56 decays into the isotope cobalt 56. By what process will this decay occur? So it looks like a beta decay. There's the beta decay, involves an electron and an antineutrino. Measuring nuclear decay. Imagine that you are studying a sample of radioactive material. You know that the atoms in the material are decaying into other types of atoms. How many of the unstable parent atoms remain after a certain amount of time? Did you know that in 1898, Marie and Pierre Curie discovered two previously unknown elements, polonium and radium, both of which were radioactive? They were awarded the Nobel Prize in Physics in 1903 for their studies of radioactive substances. The decay constant indicates the rate of radioactive decay. If the sample contains n radioactive parent nuclei at some instant, the number of parent nuclei that decay into the daughter nuclei change in n in a small time interval delta t is proportional to n as follows. Delta n equals negative lambda n delta t. The negative sign signifies that n decreases with time. That is, delta n is negative. The quantity lambda is called the decay constant. The value of lambda for any isotope indicates the rate at which that isotope decays. Isotopes with a large decay constant decay quickly, and those with a small decay constant decay slowly. The number of decays per unit time is called the decay rate, or activity of the sample. Note that the activity of the sample equals the decay constant times the number of radioactive nuclei in the sample as follows. So the activity equals the negative ratio of delta n over delta t, which equals lambda times n. The SI unit of activity is the becquerel, or BQ. 1 becquerel is equal to 1 decay per second. The Curie, or CI, which was the original unit of activity, is the approximate activity of 1 gram of radium. 1 Curie is equal to 3.7 times 10 to the 10th becquerel. Half-life measures how long it takes half a sample to decay. Another quantity that is useful for characterizing radioactive decay is written as T sub 1/2. The half-life of a radioactive substance is the time it takes for half of the radioactive nuclei in a sample to decay. The half-life of any substance is inversely proportional to the decay constant of the substance. Students might not understand that every substance has a decay constant lambda, but that the decay rate or activity is not constant. A numerical example can help them see that the activity depends on the number of radioactive nuclei in the sample at some instant. Ask students to compare the activity for two samples of radium. Lambda 1.4 times 10 to the negative 11th seconds to the negative 1. Sample A contains 5.0 times 10 to the 15 radioactive nuclei, and sample B contains 2.0 times 10 to the 18 radioactive nuclei. Using lambda n, students will find that A's activity is 7.0 times 10 to the 4th becquerel, while B's activity is 2.8 times 10 to the 7th becquerel. Also emphasize that half-life does not depend on the size of the sample. For example, any sample of carbon-14 has a half-life of 5,715 years. Conceptual challenge. Decay series. Suppose a radioactive parent substance with a very long half-life has a daughter with a very short half-life. Describe what happens to a freshly purified sample of the parent substance. Probability of decay. The more probable the decay, the shorter the half-life. Explain the statement. 3. Decay of radium. The radioactive nucleus, radium-226, has a half-life of about 1.6 times 10 to the 3 years. Although the solar system is approximately 5 billion years old, we still find this radium nuclei in nature. Explain how this is possible. The answers: Decay Series. The parent substance will decay very slowly. Many of its nuclei will remain undecayed for a long period of time. As soon as some of its nuclei have decayed, the daughter nuclei will decay rapidly. Probability of decay. As the probability of decay increases, the amount of nuclei that decays per unit of time increases, so it takes less time for the sample to decay. Decay of radium. Other elements with longer half-lives decay into radium-226. Substances with very large decay constants have short half-lives. The relationship between half-life and decay constant is given in the equation below. A derivation of this equation is beyond the scope of this book, but it involves the natural logarithm of 2. Because the natural log of 2 is 0.693, this factor occurs in the final equation. Half-life equals 0.693 over lambda. Half-life equals 0.693 divided by decay constant. Consider a sample that begins with n radioactive nuclei. By definition, after one half-life, 1/2 n, radioactive nuclei remain. After 2 half-lives, half of these will have decayed, so 1/4 n radioactive nuclei remain. After 3 half-lives, 1/8 n will remain, and so on. The half-life of the radioactive radium-226 nucleus is 5 times 10 to the 10 seconds. A sample contains 3 times 10 to the 16 nuclei. What is the decay constant for this decay? How many radium nuclei in curies will decay per second? Now let's look at what's given. The half-life is given in the problem. The n is given, the number of nuclei. The unknown, what is it we're looking for? We're looking for lambda. And we're looking for the activity. Choose an equation or situation. To find the decay constant, use the equation for half-life, which is listed. Half-life is equal to 0.693 over lambda. The number of nuclei that decay per second is given by the equation for the activity of a sample. Activity equals lambda n. Rearrange the equation and isolate the unknown. The first equation must rearrange to isolate the decay constant lambda. So lambda equals 0.693 over half-life, and you're going to plug in the half-life and crank out 1.4 times 10 to the negative 11 seconds to the negative 1. And therefore, the activity is going to be equal to, because you're going to plug in for lambda and then put in the conversion factor, and you will obtain 1.1 times 10 to the negative 5th curies. Always pay attention to units. Here the activity is divided by the conversion factor, 3.7 times 10 to the 10th seconds to the negative 1 per curie, to convert the answer from becquerels to curies as specified in the problem statement. Because the half-life is on the order of 10 to the 10 seconds, the decay constant, which approximately equals 0.7 divided by the half-life, should equal a little less than 10 to the negative 10 seconds to the negative 1. Thus, 1.4 times 10 to the negative 11 seconds to the negative 1 is a reasonable answer for the decay constant. So the activity is 1.1 times 10 to the negative fifth curies. The half-life of polonium-214 is 164 microseconds. A polonium-214 sample contains 2.0 times 10 to the sixth nuclei. What is the decay constant for the decay, and how many polonium nuclei in curies will decay per second? Okay, so let's find the equation for half-life, which contains lambda. We're going to plug in lambda, and we're going to come up with the half-life. So now we want to find the activity, which is lambda n, and we'll plug in including the conversion factor, and the activity is going to be 0.23 curies. The half-life of bismuth-214 is 19.7 seconds. A bismuth-214 sample contains 2 times 10 to the ninth nuclei. What is the decay constant for the decay, and how many bismuth nuclei in curies will decay per second? So there's the equation for half-life. Here's the given. There's the n. And there is the equation rearranged. So let's plug in. There is the number of seconds, and there is lambda. Now, there's lambda. Now we want to find the activity, which is lambda n. So we have n and we have lambda. We'll plug in, including the conversion factor, and we will find 3.2 times 10 to the negative fifth curies. The half-life of iodine-131 is 8.07 days. Calculate the decay constant for this isotope. What is the activity in curies for a sample that contains 2.5 times 10 to the 10th iodine-131 nuclei? There's the half-life, 8.07 days. Change it to seconds, and you get 6.97 times 10 to the fifth seconds. There is n, 2.5 times 10 to the 10th, and there's the equation for lambda. Plug into lambda the number of seconds, the half-life, and you get 9.94 times 10 to the negative 7th seconds, negative 1. Activity, plug in, put in the conversion factor, and you get 6.7 times 10 to the negative 7th curies for lambda. Suppose that you start with 1 times 10 to the negative 3 grams of pure radioactive substance and determine 2 hours later that only 0.25 times 10 to the negative 3 grams of the substance is left to decay. What is the half-life of this substance? Mi, T, Mf. Now I have 1/4 times 2 equals 1/2. So we know that 2 half-lives have passed in 2 hours. So the half-life is going to be 1 hour. Radon-222 is a radioactive gas with a half-life of 3.82 days. A gas sample contains 4 times 10 to the 8th radon atoms initially. Estimate how many radon atoms will remain after 12 days. There is the half-life. There is n. So we know that we have 12 days, so we had 3 half-lives. And so we know that 1/8 of the total n is going to be 5 times 10 to the 7th atoms. Estimate how many radon nuclei will have decayed by this time. So we want to simply subtract, and we find that the answer is 3.5 times 10 to the 8th atoms. A decay curve is a plot of the number of radioactive parent nuclei remaining in a sample as a function of time. A typical decay curve for a radioactive sample is shown in Figure 7. After each half-life, half the remaining parent nuclei have decayed. This is representative in the circles to the right of the decay curve. Some students may think that the half-life time is half of the time it takes for the sample to be used up. Ask students how many radioactive nuclei out of 600 are left after 2.0 hours. If the half-life is 1 hour, that would give 150 left over. The blue spheres are the parent nuclei, carbon-14, and the red spheres are daughter nuclei, nitrogen-14. Figure 7, the radioactive isotope carbon-14 has a half-life of 5,715 years. In each successive 5,515 year period, half the remaining carbon-14 nuclei decay to nitrogen-14. This is visual strategy for figure 7. Be sure students interpret the graph properly. Given that the half-life of C14 is 5,715 years, what years are shown on the graph points? The answer: 0, 5,715, 11,430, and 17,145. If the initial sample contained 80,000 radioactive nuclei, when would it fall below 20,000 nuclei? After 11,430 years, 2 half-lives. And that's after. Measuring the ratio between carbon-14, which decays as shown in figure 7, and carbon-12, which does not decay, provides an approximate date as to when the organism was alive. Section review. Explain the main differences between alpha, beta, and gamma decays. In alpha decay, helium particles are emitted. In beta, electrons or positrons are emitted. In gamma, photons are emitted. In alpha and beta, a new element is produced. In gamma, energy is lost. Complete the following radioactive decay formulas. Fairly straightforward. I'll kind of hang out here. Okay, and that's it. A radioactive sample of 5.3 times 10 to the 5th nuclei, there is 1 decay every 4.2 hours. What is the decay constant for the sample? So what are we actually trying to solve for? I think we're trying to solve for just a very quick lambda. So plug in, list everything, plug in, and there you have it. What is the half-life for the sample? Again, list everything. And you have the activity now. The activity constant. So the half-life is 1.2 times 10 to the 9th seconds. And then you can convert that to days or years or whatever is convenient. And you get 180 years. Critical thinking, the carbon-14 content decreases after the death of a living system with a half-life of 5,715 years. If an archaeologist finds an ancient fire pit containing partially consumed firewood, and if the carbon-14 content of the wood is only 12.5%, that of an equal carbon sample from a present-day tree, what is the age of the ancient site? List everything. (17,140 years). Section 3, Nuclear Reactions. Distinguish between nuclear fission and nuclear fusion. Explain how a chain reaction is utilized by nuclear reactors. Compare fission and fusion reactors. Any process that involves a change in the nucleus of an atom is called a nuclear reaction. Nuclear reactions include fission, in which a nucleus splits into two or more nuclei, and fusion, in which two or more nuclei combine. Stable nuclei can be converted to unstable nuclei. When a nucleus is bombarded with energetic particles, it may capture a particle, such as a neutron. As a result, the nucleus will no longer be stable and will disintegrate. For example, protons can be released when alpha particles collide with nitrogen atoms as follows. The helium atom plus the nitrogen 14 will yield X plus hydrogen. According to this expression, an alpha particle strikes a nitrogen nucleus and produces an unknown product, nucleus X, and a proton. By balancing atomic numbers and mass numbers, we can conclude that the unknown product of a mass number of 17 and an atomic number of 8. Because the element with an atomic number of 8 is oxygen, the product can be written symbolically as oxygen 17, and the reaction can be written as follows. This nuclear reaction starts with two stable isotopes, helium and nitrogen, that form an unstable intermediate nucleus, fluorine. The intermediate nucleus then disintegrates into two different stable isotopes, hydrogen and oxygen. This reaction, which was the first nuclear reaction to be observed, was detected by Rutherford in 1919. Heavy nuclei can undergo nuclear fission. Nuclear fission occurs when a heavy nucleus splits into two lighter nuclei. For fission to occur naturally, the nucleus must release energy. This means that the nucleons in the daughter nuclei must be more tightly bound and therefore have less mass than the nucleons in the parent nucleus. This decrease in mass per nucleon appears as released energy when fission occurs. Often it forms such as photons or kinetic energy of the fission products. Figure 8, light nuclei are very loosely bound. The binding energy of heavy nuclei is roughly the same for all nuclei. Figure 8, visual strategy. Point out that the graph represents empirical information about energy of all known nuclei, including isotopes of mass numbers A1 to A230, approximately. Question 1. According to the graph, what is the average binding energy per nucleon of the most stable nucleus? About 8.5 mega electron volts per nucleon. That's considerable. Suppose a nucleus of mass number A24 splits into two nuclei of equal masses. Determine the approximate binding energy per nucleon for each daughter nucleus. About 7 mega electron volts. This is less than the binding energy per nucleon of the parent, so the daughter nuclei will be less stable. This example illustrates why nuclei with A less than 58 do not undergo fission. Repeat the last exercise with a parent nucleus of A equals 200, about 8.5 mega electron volts. In this case, the binding energy per nucleon increases after fission. Because fission produces lighter nuclei, the binding energy per nucleon must increase with decreasing atomic number. Figure 8 shows that is possible only for atoms in which A is greater than 58. Thus, fission occurs naturally only for heavy atoms. One example of this is the fission of uranium-235. First, the nucleus is bombarded with neutrons. When the nucleus absorbs a neutron, it becomes unstable and decays. The fission of 235 can be represented as follows. The isotope, uranium-236, is an intermediate state that lasts only for about 10 to the negative 12th seconds before splitting into X and Y. Many combinations of X and Y are possible. In the fission of uranium, about 90 different daughter nuclei can be formed. The process also results in the production of about 2 or 3 neutrons per fission event. And that's what causes the chain reaction. A typical reaction of this type is as follows. To estimate the energy released in a typical fission process, note that the binding energy per nucleon is about 7.6 mega electron volts. For heavy nuclei, those having a mass number of approximately 240, and about 8.5 mega electron volts for nuclei of intermediate mass. See figure 8 on the previous page. The amount of energy released in a fission event is the difference in these binding energies. 8.5 mega electron volts minus 7.6 mega electron volts, or about 0.9 mega electron volts per nucleon. Assuming a total of 240 nucleons, this is about 220 mega electron volts. Remind students that the upper number next to the element symbol is the mass number, and that the lower number indicates the number of protons. Also remind them that these equations show the conservation of nucleon number and charge in a nuclear reaction. Ask how many protons are found in the parent and in the daughters in the nuclear fission of uranium-235. 0 plus 92 equals 56 plus 36 plus 0. How many nucleons are found in each? 1 plus 235 equals 140 plus 93 plus 3 times 1. Figure 9, a nuclear chain reaction can be initiated by the capture of a neutron. This is a very large amount of energy relative to the energy released in a typical chemical reaction. For example, the energy released in burning 1 molecule of octane used in gasoline engines is about 100 millionth the energy released in a single fission event. Neutrons released in fission can trigger a chain reaction. When uranium-235 undergoes fission, an average of about 2.5 neutrons are emitted per event. The released neutrons can be captured by other nuclei, making these nuclei unstable. This triggers additional fission events, which lead to the possibility of a chain reaction, as shown in Figure 9. Calculations show that if the chain reaction is not controlled, that is, if it does not proceed slowly, it could result in the release of an enormous amount of energy and a violent explosion. If the energy in 1 kilogram of uranium-235 were released, it would equal the energy released by the detonation of 20,000 tons of TNT. This is the principle behind the first nuclear bomb, shown in Figure 10, which was essentially an uncontrolled fission reaction. Students may wonder about the meaning of an average of about 2.5 neutrons being emitted when uranium-235 undergoes fission, as described in the last paragraph on this student page. Point out that the products of uranium-235 fission may be different daughter nuclei than those shown in the diagram. Some reactions release 3 neutrons while others release 2. Have students find an example of each in Figure 9. A 3-neutron reaction would be 1 neutron plus uranium-235 yields cesium-144 and lanthanum-90 plus 2 neutrons. 2 neutrons would be 1 neutron plus uranium-235 yields bromine-87 and lanthanum-146 plus 3 neutrons. The first nuclear fission bomb, often called the atomic bomb, was tested in New Mexico in 1945, Alamogordo, New Mexico. The nuclear reaction is a system designed to maintain a controlled, self-sustained chain reaction. Such a system was first achieved with uranium as a fuel in 1942 by Enrico Fermi at the University of Chicago. Primarily, it is the uranium-235 isotope that releases energy through nuclear fission. What has been called the atomic bomb since 1945 is actually a tremendous nuclear fission reaction. Likewise, the so-called hydrogen bomb is an uncontrolled nuclear fusion reaction in which hydrogen nuclei merge to form helium nuclei. Uranium from ore typically contains about 0.7% uranium-235, with the remaining 99.7% being the uranium-238 isotope. Because uranium-238 tends to absorb neutrons without fissioning, reactor fuels must be processed to increase the proportion of uranium-235 so that the reaction can sustain itself. This process is called enrichment. At this time, all nuclear reactors operate through fission. One difficulty associated with fission reactors is the safe disposal of radioactive materials when the core is replaced. The terms atomic bomb and hydrogen bomb are misleading because terms associated with atoms and elements are used to detonate nuclear reactions. Students should be reminded that the order of magnitude of energies at the nuclear level is 1,000,000 times higher than it is at the atomic level. Transportation of reactor fuel and reactor waste poses safety risks. As with all energy sources, the risks must be weighed against the benefits and the availability of the energy source. Light nuclei can undergo nuclear fusion. Nuclear fusion occurs when 2 light nuclei combine to form a heavier nucleus. As with fission, the product of fusion event must have a greater binding energy than the original nuclei for energy to be released in the reaction. Because fusion reaction produces heavier nuclei, the binding energy per nucleon must increase as atomic number increases. As shown in Figure 8, that is possible only for atoms with A is less than 58. Hence, fusion occurs naturally only for light atoms. One example of this process is the fusion reaction that occur in stars. All stars generate energy through fusion. About 90% of stars, including our sun, fuse hydrogen and possibly helium. Some other stars fuse helium or other heavier elements. The proton-proton cycle is a series of 3 nuclear fusion reactions that are believed to be stages in the liberation of energy in our sun and other stars rich in hydrogen. In the proton-proton cycle, 4 protons combine to form an alpha particle and 2 positrons, releasing 25 mega electron volts of energy in the process. The first 2 steps in the cycles are as follows. I'm not going to read the reactions. This is followed by either of the following processes. The released energy is carried primarily by gamma rays, positrons, and neutrinos. These energy liberating fusion reactions are called thermonuclear fusion reactions. The hydrogen fusion bomb, first detonated in 1952, is an example of an uncontrolled thermonuclear fusion reaction. A mushroom cloud from the world's first successful hydrogen bomb test on November 1st, 1952. Credit public domain. Fusion reactors are being developed. The enormous amount of energy released in fusion reactions suggests the possibility of harnessing this energy for useful purposes on Earth. Efforts are underway to create controlled thermonuclear reactions in the form of a fusion reactor. Because of the ready availability of its fuel source, water, controlled fusion is often called the ultimate energy source. For example, if deuterium, hydrogen 2, were used as the fuel, 0.6 grams of deuterium could be extracted from just 1 liter of water at a cost of about 1 cent. Such rates would make the fuel cost of even an inefficient reactor almost insignificant. The proton-proton cycle shows that the end product of fusion of hydrogen nuclei is safe, non-radioactive helium. Unfortunately, a thermonuclear reactor that can deliver a net power output for an extended time is not yet a reality. Many difficulties must be resolved before a successful device is constructed. For example, the energy released in a gas undergoing nuclear fusion depends on the number of fusion reactions that can occur in a given amount of time. This varies with the density of the gas because collisions are more frequent in a denser gas. It also depends on the amount of time the gas is confined. In addition, the Coulomb repulsion force between 2 charged nuclei must be overcome before they can fuse. The fundamental challenge is to give the nuclei enough kinetic energy to overcome this repulsive force. This can be accomplished by heating the fuel to extremely high temperatures, about 10 to the 8th K, or about 10 times greater than the interior temperatures of the sun. Such high temperatures are difficult and expensive to obtain in a laboratory or a power plant. An enormous eruption of solar material called a coronal mass ejection spreading out into space. Section Review. What are the similarities and differences between fission and fusion? Both are nuclear reactions that release energy. In fission, a heavy nucleus splits. In fusion, two light nuclei combine. Explain how nuclear reactions utilize chain reactions. The excess neutrons produced by each reaction are used to induce additional reactions. What is enrichment? Why is enrichment necessary when uranium is used as a reactor fuel? Enrichment is the process of increasing the amount of uranium-235 in reactor fuels. This is necessary because uranium from ore contains mostly uranium-238. A fission reaction leads to the formation of barium-141 and krypton-92 when uranium-235 absorbs a neutron. How is this reaction expressed symbolically? One neutron plus uranium-235 yields barium-141 plus krypton-92 plus 3 neutrons. How many neutrons are released in this reaction? 3 neutrons. What are some advantages of fusion reactors as opposed to fission reactors? What are some difficulties in the development of a fusion reactor? Fusion reactors produce less radioactive waste and the fuel water is plentiful. Difficulties include the high temperatures and densities necessary to achieve controlled fusion reactions. Why would a fusion reactor produce less radioactive waste material than a fission reactor does? A fusion reactor would produce less radioactive waste than a fission reactor does because fusion produces more stable nuclei than fission does. Particle Physics, Section 4. Define the 4 fundamental interactions of nature. Identify the elementary particles that make up matter. And last, describe the standard model of the universe. Particle view of nature. Particle physics seeks to discover the ultimate structure of matter, elementary particles. Elementary particles, which are the fundamental units that compose matter, do not appear to be divisible and have neither size nor structure. Look down below. Many new particles have been produced in accelerators. Until 1932, scientists thought protons and electrons were elementary particles because these particles were stable. Misconception alert. Students will be familiar with electric and gravitational forces, but may not have a clear idea of how the two compare with one another. Point out that these two forces differ in order of magnitude. The Stanford Linear Accelerator in California creates high-energy particle collisions that provide evidence of new particles. Many new particles have been produced in accelerators. However, beginning in 1945, experiments at particle accelerators such as the Stanford Linear Accelerator, shown in Figure 11, have demonstrated that new particles are often formed in high-energy collisions between known particles. These new particles tend to be very unstable and have very short half-lives, ranging from 10 to the negative 6 to 10 to the negative 23rd seconds. So far, more than 300 new particles have been cataloged. There are 4 fundamental interactions in nature. The key to understanding the properties of elementary particles is to be able to describe the interactions between them. All particles in nature are subject to 4 fundamental interactions: strong, electromagnetic, weak, and gravitational. The strong interaction is responsible for binding of neutrons and protons into nuclei, as we have seen. This interaction, which represents the glue that holds the nucleons together, is the strongest of all the fundamental interactions. It is very short-ranged and is negligible for separations greater than 10 to the negative 15 meters, the approximate size of a nucleus. The electromagnetic interactions, which is about 10 to the negative 2 times the strength of the strong interactions at nuclear distances, is responsible for the attraction of unlike charges and the repulsion of like charges. This interaction is responsible for the binding of atoms and molecules. It is long-range interaction that decreases in strength as the inverse square of the separation between interacting particles as described in the chapter Electric Forces and Fields. The weak interactions is a short-range nuclear interaction that is involved in beta decay. Its strength is only about 10 to the negative 13 times that of a strong interaction. However, because the strength of an interaction depends on the distance through which it acts, the relative strengths of two interacting differ depend on what separation distance is used. The strength of the weak interaction, for example, is sometimes cited to be as large as 10 to the negative 6 times that of the strong interaction. Keep in mind that these relative strengths are merely estimates and they depend on the assumed separation distance. Figure 12, in particle physics, the electromagnetic interaction is modeled as an exchange of photons. The wavy red line represents a photon and the blue lines represent electrons. Finally, the gravitational interaction is a long-range interaction with a strength of only about 10 to the negative 38 times that of the strong interaction. Although this familiar interaction is what holds the planets, stars, and galaxies together, its effect on elementary particles is negligible. The gravitational interaction is the weakest of all four fundamental interactions. A force can be thought of as mediated by an exchange of particles. Notice that in this section we have referred to a force as an interaction. This is because in particle physics the interaction of matter is usually described not in terms of forces but in terms of the exchange of special particles. In the case of electromagnetic interactions, the particles are photons. The particles are photons. Figure 12 shows how two electrons might repel each other through the exchange of a photon. A simple diagram representing the interaction between two particles is called a Feynman diagram. Such diagrams are named after the American scientist Richard P. Feynman, 1918 to 1988, who developed them. Figure 12 is an example of a Feynman diagram. Because momentum is conserved, the electrons emitting a photon changes direction slightly. As the photon is absorbed, the two electron directions must also change. The net effect is that the two electrons change direction and move away from each other. Strong, electromagnetic, weak, and gravitational. The fundamental interactions of nature. Table 6, very informative, keeps things organized, most excellent. Likewise, the strong interactions is mediated by particles called gluons. The weak interaction is mediated by particles called the W and Z bosons. And the gravitational interaction is mediated by gravitons. All of these except gravitons have been detected. The four fundamental interactions of nature and their mediating field particles are summarized in Table 6. Classification of particles. All particles other than the mediating field particles can be classified into two broad categories, leptons and hadrons. The difference between the two is whether they interact through the strong interaction. Leptons are a group of particles that participate in the weak gravitational and electromagnetic interactions, but not in the strong interactions. Hadrons are particles that interact through all four fundamental interactions, including the strong interaction. The interaction of charged particles by the exchange of photons is described by a theory called quantum electrodynamics, or QED. Leptons are thought to be elementary particles. Electrons and neutrinos are both leptons. Like all leptons, they have no measurable size or internal structure and do not seem to break down into smaller units. Because of this, leptons appear to be truly elementary. The number of known leptons is small. Currently, scientists believe that there are only 6 leptons: the electron, the muon, the tau, and the neutrino associated with each. Each of these 6 leptons also have an antiparticle. Hadrons include mesons and baryons. Hadrons and strongly interacting particles can be further divided into 2 classes, mesons and baryons. Originally, mesons and baryons were classified according to their masses. Baryons were heavier than mesons, and both were heavier than leptons. Students might not differentiate clearly between the mediating field particles and classification of other particles. To build on their prior knowledge suggests that they classify the particles they already know into 2 groups using the following system. Building blocks, or particles of matter, interact with, attract, or repel other particles of matter. They may or may not be broken into smaller particles that will in turn attract and repel each other. Mediating field particles serve as messengers of the forces between the building blocks of matter. Figure 13. Leptons appear to be elementary, while hadrons consist of smaller particles called quarks. As a result, hadrons can be further subdivided into baryons and mesons based on their internal composition. However, this distinction no longer holds. Today, mesons and baryons are distinguished by their internal structure. All mesons are unstable. Because of this, they are not constituents of normal everyday matter. Baryons have masses equal to or greater than the proton mass. The most common examples of baryons are protons and neutrons, which are constituents of normal everyday matter. A summary of this classification of particles is given in Figure 13. Hadrons are thought to be made of quarks. Particle collision experiments involving hadrons seem to involve many short-lived particles, implying that hadrons are made up of more fundamental particles. Furthermore, there are numerous hadrons, and many of them are known to decay into other hadrons. These facts strongly suggest that hadrons, unlike leptons, cannot be truly elementary. In 1963, Murray Gell-Mann and George Vague independently proposed that hadrons have a more elementary substructure. According to their model, all hadrons are composed of 2 or 3 fundamental particles, which came to be called quarks. In the original model, there were 3 types of quarks designated by the symbols U, D, and S. These were given the arbitrary names up, down, and sideways, now more commonly referred to as strange. Associated with quarks is an antiquark of opposite charge. The difference between mesons and baryons is due to the number of quarks that compose them. The compositions of all hadrons known when Gell-Mann and Zweig presented their models could be completely specified by 3 simple rules, which summarized in Table 7. Mesons, 1 quark and 1 antiquark; baryon, 3 quarks; and antibaryon, 3 antiquarks. Later evidence from collision experiments encouraged theorists to propose the existence of 3 more quarks, now known as charm, top, and bottom. These 6 quarks seem to fit together in pairs: up, down, charm, strange, and top and bottom. Table 8, quarks and their charges, up, down, charm, strange, top, and bottom, are all summarized in Table 8. Study it carefully and notice the antiquark as well. The charge of the hadron is equal to the sum of the charges of its constituent quarks and is either 0 or a multiple of E, the fundamental unit of charge. This implies that quarks have a very unusual property, fractional electric charge. In other words, the charge of the electron is no longer thought to be the smallest possible non-zero charge that a particle can have. The charge for all 6 quarks that have been discovered and their corresponding antiquarks are summarized in Table 8. Did you know Murray-Gell-Mann borrowed the word quark from the passage 3 quarks for a muster mark in James Joyce's book Finnegan's Wake? Conceptual challenge: particle-antiparticle interactions. An antibyron interacts with a meson. Can a byron be produced in such an interaction? Explain. And strong and weak interactions. 2 protons in a nucleus interact via the strong interactions. Are they also subject to weak interactions? Particle-antiparticle interactions? No. An antibyron is made of 3 antiquarks, and a meson is made of 1 quark and 1 antiquark. Thus, a baryon, which consists of 3 quarks, could not be produced in this reaction. Strong and weak interactions. Yes, although the strong interaction has a much greater effect. Baryons contain 3 quarks, while mesons contain a quark and an antiquark. The barons represented are a proton and a neutron. The mesons shown are a pion and a kaon, both rare particles. Figure 14, visual strategy. Explain that although many of the quarks have the same charge, they have special properties called flavor and color that make them different. Question: what is the charge of a pi plus meson shown in figure 14? Answer: 1 electron, because it's plus 2/3 E plus 1/3 E equals 1 E. Figure 14 represents the quark compositions of several hadrons, both baryons and mesons. Just 2 of the quarks, U and D, are needed to construct the hadrons encountered in ordinary matter, protons and neutrons. The other quarks are needed only to construct rare forms of matter that are typically found only in high-energy situations, such as particle collisions. The charges of the quarks that make up each hadron in Figure 14 add up to 0 or a multiple of E. For example, the proton contains 3 quarks, U, U, and D, having charges of plus 2/3 E, plus 2/3 E, and negative 1/3 E. The total charge of the proton is plus E, as you would expect. Likewise, the total charge of quarks in a neutron is 0, plus 2/3 E, minus 1/3 E, and minus 1/3 E. You may be wondering whether such discoveries will ever end. At present, physicists believe that 6 quarks and 6 leptons and their antiparticles are the fundamental particles. Did you know the word atom is from the Greek word atomos, meaning indivisible? At one time, atoms were thought to be the indivisible constituent of matter. That is, they were regarded as elementary particles. Today, quarks and leptons are considered to be elementary particles. Despite many extensive efforts, no isolated quark has ever been observed. Physicists now believe that quarks are permanently confined inside ordinary particles by the strong force. This force is often called the color force for quarks. The Greek letter mu represents muon particles, and the Greek letter nu designates neutrino particles. The symbol nu e and nu mu and nu tau represent the neutrinos associated with the electron, the muon and the tau, respectively. Of course, quarks are not really colored. Color is merely a name given to the property of quarks that allows them to attract one another and form composite particles. The attractive force between nucleons is a byproduct of the strong force between quarks. This schematic diagram summarizes the main elements of the standard model, including the fundamental forces, the mediating field particles, and the constituents of matter. This is figure 15. Study it carefully, very informative. Figure 15, visual strategy. Use the following questions to make sure students interpret the information in figure 15 properly. Which forces hold quarks together? Which forces hold quarks together? Gravitational force, the weak force, the electromagnetic force, and the strong force, the most significant force. Which field particles mediate the interaction between neutrinos? Photons, W and Z bosons, and gravitons. Which particles are held together by gluons? Are held together by gluons. Quarks are held together by gluons. The standard model. Current model used in particle physics to understand matter is called the Standard Model. This model was developed over many years by a variety of people. Although the details of the Standard Model are complex, the model's essential elements can be summarized by using figure 15. According to the Standard Model, the strong force is mediated by gluons. The force holds quarks together to form composite particles such as protons, neutrons, and mesons. Leptons participate only in the electromagnetic, gravitational, and weak interactions. The combination of composite particles such as protons and neutrons with leptons such as electrons makes the constituents of all matter, which are atoms. The Standard Model, very important. The Standard Model can help explain the early universe. Particle physics helps us understand the evolution of the universe. If we extrapolate our knowledge of the history of the universe, we find that time itself goes back only about 13 billion to 15 billion years. At that time, the universe was inconceivably dense. In the brief instant after this singular moment, the universe expanded rapidly in an event called the Big Bang. Immediately afterward, there were such extremes in the density of matter and the energy that all four fundamental interactions of physics operated in a single unified way. The temperatures and energy present reduced everything into undifferentiated quark soup. Figure 16, the four fundamental particles of nature were indistinguishable during the early moments of the Big Bang. Study carefully. We will do a visual strategy on figure 16, visual strategy. Be sure students correctly interpret the information presented in figure 16. That's why we're doing a visual strategy. What did the strong force and the electro-weak force separate? at approximately 10 to the negative 3 seconds. Which of the colored sections shown in the figure occurred during the first second after the Big Bang? The red sections, the yellow sections, and the green sections, and part of the blue section. According to this figure, what is the present age of the universe? Approximately 10 to the 18 seconds. The age of the universe is approximately 10 to the 18th seconds. The evolution of the four fundamental interactions from the Big Bang to the present is shown in Figure 16. During the first 10 to the 43 seconds, it is presumed that the strong electroweak, electromagnetic end weak, and gravitational interactions were joined together from 10 to the negative 43 seconds to 10 to the negative 32 seconds. After the Big Bang, gravity broke free of this unification while the strong and electroweak interactions remain as one. For students, the term Big Bang may conjure up images of a vast explosion of a bomb, emphasize that the Big Bang was extremely rapid, but was not destructive or violent. This was a period when particle energies were so great, greater than 10 to the 16 giga electron volts, that very massive particles that are now rare, as well as quarks, leptons, and their antiparticles, existed. Then the universe rapidly expanded and cooled. The strong and weak electroweak interactions parted, and the grand unification was broken. About 10 to the negative 10th seconds after the Big Bang, as the universe continued to cool, the electroweak interactions split into the weak interactions and the electromagnetic interactions. Until about 7 times 10 to the 5th years, 2 times 10 to the 13th seconds, after the Big Bang, most of the energy in the universe was in the form of radiation rather than matter. This was the era of the radiation-dominated universe. Such intense radiation prevented matter from forming even single hydrogen atoms. Matter did exist, but only in a few of ions and electrons. Electrons are strong scatterers of photons, so matter at this time was opaque to radiation. Matter continuously absorbed and re-emitted photons, thereby ensuring thermal equilibrium of radiation and matter. By the time the universe was about 380,000 years old, it had expanded and cooled to about 3000 K. At this temperature, protons could bind to electrons to form hydrogen atoms. Without free electrons to scatter photons, the universe suddenly became transparent. Matter and radiation no longer interacted as strongly, and each evolved separately. By this time, most of the energy in the universe was in the form of matter. Clumps of neutral matter steadily grew. First atoms, followed by molecules, gas clouds, stars, and finally galaxies. This period, referred to as the matter-dominated universe, continues to this day. The standard model is still incomplete. While particle physicists have been exploring the realm of the very small, cosmologists have been exploring cosmic history back to the first microsecond of the Big Bang. Observation of the event that occurs when two particles collide in an accelerator is essential to reconstructing the early moments in cosmic history. Perhaps the key to understanding the early universe is to first understand the world of elementary particles. Cosmologists and particle physicists find that they have many common goals, and they are working together to attempt to study the physical world at its most fundamental level. Our understanding of physics at short distances is far from complete. Particle physics still faces many questions. For example, why does the photon have no mass? Why, while the W and Z bosons do? Because of this mass difference, the electromagnetic and weak forces are quite distinct at low energies, such as those in everyday life, but they behave in similar ways at very high energies. To account for these changes, the Standard Model proposes the existence of a particle called the Higgs Boson, which exists only at high energies at which electromagnetic and weak forces begin to merge. The Higgs boson has not yet been found. According to the Standard Model, its mass should be less than 1 tera-electron volt. International efforts are underway to build a device capable of reaching energies close to 1 tera-electron volt to search for the Higgs boson. There are still other questions that the Standard Model has yet to answer. Is it possible to unify the strong and electroweak theories in a logical and consistent manner? Why do quarks and leptons form three similar but distinct families? Are muons the same as electrons apart from their different masses? Or do they have other subtle differences that have yet been detected? Why are some particles charged and others neutral? Why do quarks carry a fractional charge? What determines the masses of the fundamental constituents? Can isolated quarks exist? The questions go on and on. Because of the rapid advances and new discoveries in the field of particle physics, by the time you read this book, some of these questions may have been resolved, while new questions may have emerged. Name the four fundamental interactions in particles that mediate each interaction. The strong force is mediated by gluons. The electromagnetic force is mediated by photons. The weak force is mediated by W and Z bosons. And gravity is mediated by gravitons. What are the differences between hadrons and leptons? What are the differences between baryons and mesons? Curious, very curious. Hadrons consist of quarks, while leptons are thought to be indivisible. Hadrons interact with gluons, the strong interaction, but leptons do not. Mesons consist of one quark and one antiquark, and baryons consist of 3 quarks. Describe the main stages of the evolution of the universe according to the Big Bang theory. Up to 10 to the negative 43 seconds, all forces were unified. At 10 to the negative 43 seconds, gravity broke free. At 10 to the negative 32 seconds, the strong force broke free. And at 10 to the negative 10 seconds, the weak force broke free. From 10 to the negative 43 seconds to 10 to the negative 32 seconds, quarks, leptons, and their antiparticles existed. Until 7 times 10 to the 5th years, most energy was in the form of radiation. At 380,000 years, atoms began forming. And soon, most energy was in the form of matter, as it is today. Key ideas, Section 1, the nucleus. The nucleus consists of protons and neutrons. It is small, dense core of an atom. A nucleus can be characterized by a mass number A, an atomic number Z, and a neutron number N. The binding energy of a nucleus is the difference in energy between its nucleons when bound and its nucleons when unbound. Section 2. The unstable nucleus can decay in 3 ways. This is Section 2, nuclear decay. Alpha decay, beta decay, and gamma decay. The decay constant indicates the rate of radioactive decay. The half-life is the time required for half the original nuclei of a radioactive substance to undergo radioactive decay. Section 3, nuclear interactions. Nuclear interactions involve a change in the nucleus of an atom. In fission, a heavy nucleus splits into two lighter nuclei. In fusion, two light nuclei combine to form a heavier nucleus. Section 4, particle physics. There are four fundamental interactions in nature: strong, weak, gravitational, and electromagnetic. The constituents of matter can be classified as leptons or hadrons, and hadrons can be further subdivided into mesons and baryons. Electrons and neutrinos are leptons. Protons and neutrons are baryons. Mesons consist of quark and antiquark pairs. Baryons consist of 3 quarks.